Okay, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Had a bit of computer trouble there, so let's not waste any more time and just jump right into it. I actually got mixed up today because, as you guys know, I'm teaching like two sections of this class. And so it's Math 1203, R04, Math 1203, LO1. And I think I was teaching the LO1 class, but I clicked on the tab for your class by accident. And so I did a bunch of things with them that I thought now that I did with you because it was in your section under your tab with your class label. And I did that with them. Okay, I guess I'll move on to the next topic. But it turns out, no, I did that with the other class. So now I'm going to teach you something that I thought I taught you before, but I didn't teach you before. I taught the other class before. So that is marginal analysis. Like we didn't do that, right? Just to make sure we didn't do marginal analysis. Last thing we did was linear approximation. Okay, awesome. So last time, the last thing you should remember is when we did linear approximation, where we kind of use a tangent line to approximate the output of a function. That's the main formula. This is the kind of problem that I would ask you to do. It's actually way more useful than that problem would show you, but in a Calc 1 class, that's what we can do. And with our last example, we got up to like 6 decimal place accuracy, like by our hands alone. We're not even supercomputers. Imagine what a supercomputer could do, right? So now let us move on to marginal analysis. So this is the second part of section 3.2. They're both kind of using the derivative, whether as a tangent line or just the derivative itself to approximate things. So they're both kind of similar in that sense, but they're not really similar. They will be very different. And this topic that I'm going to teach you, marginal analysis, has a lot of prerequisite knowledge that would go along with it. But of course, I'm going to tell you all the knowledge that you need to know. So let's actually move on. So this is 3.2 continued. So we're going to be doing marginal analysis. Oh. Okay, so this is pretty much an application of derivatives to economics. And so that's basically what we're going to be doing. So now let's talk about, let's kind of set this up, give you like a motivating example. Just to kind of introduce to you, like how would a derivative come into play here? Don't know why the thing does that. Okay. Just set up a motivating example just to sort of get into what we will be doing here. So suppose you have a cost function, right? So you are a business owner, you sell stuff, you have a way to calculate your costs, right? The amount of electricity you use, the space you rent, the people you hire, et cetera. And let's say you can actually track this by a function, right? So it's the pay rate times the number of people times this position plus blah, 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 right? So you can actually figure that out for your own situation. We'll call it C of X, where C of X equals the cost to produce X items. Okay, so whatever money it takes you to make X things, the function C of X does that. So it includes the labor, the materials, the whatever. we know C prime of x would be equal to the limit as h approaches 0 of C of x plus h minus C of x all over h. Now, what we're going to do is we're going to kind of ignore the limit in some sense, right? So remember, the limit is what happens as we get close, right? We get closer and closer and closer, the limit becomes the value that we're approaching. However, let's just assume that we're at a point that we already consider very close, and then we can kind of take away the limit. So this means if h is close to 0, then we can actually use this as an approximation. The derivative is going to be approximately equal to this expression on iPad. Okay, so we're just pretending that h is very small, very, very close to 0, when h is small, close to 0. Okay. Now, in an economic context, how do you spell economic? Economic context, h equals 1 is often considered small. I'm a factory that makes iPhones. How many iPhones did you make last month? 1. Well, that's small, isn't it? I mean, you might as well have made 0, I feel like, right? So in an economic context, sometimes 1 is very small. It's pretty close to 0. It's almost nothing, right? And so plugging in h equals 1 above, we get that your C prime of x is going to be approximately equal to C of x plus 1 instead of h minus C of x all over 1, which you just get that expression, right? And so we have this kind of idea here. Now I want you to realize that what this is saying, C of x plus 1, well, this is the cost to produce x plus 1 items. This is the cost to produce x items, right? So now, bring up a question to you guys. What does the right-hand side above represent? If you were to tell me in words, that expression, C of x plus 1 minus C of x, what is it telling me? What is it calculating? What information can I get from that expression?
Profit?
No, for profit, you have to know how much money you're making, right? Like there's only costs being shown here. It's always a cost function. You can't determine profit just by cost. So if I take the cost to make x plus 1 items and I subtract the cost to make x items, what does that number represent?
The cost to produce 1 item?
Almost, very close. It is the cost to produce 1 item, but which item? It actually gives you the additional cost to produce the x plus first item, right? It's the cost to produce the last item, right? So now your C of x plus 1 minus C of X. Well, this is the additional cost to produce the X plus first item, i.e., it's the additional cost to produce one more item. Yeah, so it's about producing one more item, but specifically after X items have already been produced. Okay, so it is the cost of one item, but it's the last item specifically. So if I know how much it costs me to make 11 things, and then I subtract the cost to make the first 10 things, then I would know how much the 11th thing cost, right? Because then I throw away the cost of the first 10. I'm going to be left over the cost of the 11th. Not the cost of the first, not the cost of the third, not the cost of the fifth, not the cost of any of the others, the cost of the last one specifically, the one that is so-called on the margin, right? So C prime of X, approximately C plus 1, C of X plus 1 times C of X, measures the cost to produce one more item at the margins of production. Margins is like, you know, the outer edge, like you're at the end, right? We're at X items, but we want to go one more. We want to push the envelope a little bit, push the margins. Hence, C prime of X can approximate this value. And is hence called the marginal cost. Okay, so that is the motivating example here, right? So we want to know what is the additional cost to produce one more, to just go a little bit further than we've already gone, right? That expression is something like C of X plus 1 minus C of X. However, based on what we know about the definition of the derivative, C prime is almost that number. And it turns out that that is actually very useful because a lot of the times, C prime would be easier to deal with or calculate than it would be to deal with C of X plus 1, for example. So you want to produce one more item, but you know, you're at max capacity. You have to hire another employee. You probably have to open up another location, get a larger space. Like it can be complicated to figure out how to push the margins. You know what I mean? So as opposed to actually physically having to calculate C of X plus 1 and then subtract your current cost from that, it's sometimes much more easier to, at the point of C of X, to make a projection as to what the additional cost would be. And so a derivative could be a way to do this, right? And this is what's called a marginal cost in this specific example, but you can actually do this in general. We can generalize this. Given, say, f of x, which is some function, then f prime of x is called its marginal function. In this context. So you can think of marginal function as a sort of synonym for derivative, right? It's the synonym for derivative when you're in an economics context, right? So marginal function is a synonym for derivative in an economic context. So we know a bunch of synonyms for derivatives at this point. Derivative is the same as saying slope, just in a more general way. It's the same as saying instantaneous rate of change. It's the same as saying how fast the output is changing in relation to the input. These are all different phrases for the same thing. And so now this is a new application. They call it a different name, but it's really just a derivative, right? So given any function, the derivative is its marginal function. And so if C of x is your cost function, then C prime of x is your marginal cost function. Also, if R of x is your revenue function, then R prime of x would be your marginal revenue. If P of x is equal to your profit function, P prime is, well, no one knows what this is called. I'm kidding. It's called your marginal profit function, of course. Right? So, and of course, et cetera, et cetera, et cetera. Right? So marginal function just means the derivative. But when you use the phrase marginal, it brings with it a certain connotation. Everyone knows what context you're talking about. Oh, you're talking about if you produce something, you just want to kind of figure out how much to produce a little more, how much to produce one more specifically in Calculus 1 class. And so everyone kind of knows what context you're thinking of using the derivative in when you say marginal. Let's make sure that I have enough time. Okay, so yeah, now, yeah, so et cetera, you get the idea. Now, since we're doing economics applications, there are some things about economics that you should know. So let's actually deal with that. Economic functions to know. Okay, so there's C of x, the cost function. Right? Now, what is important about the cost function for us is that it's never going to be something that you have to calculate, right? It's always going to be given. For this class, this will always be given when needed. In practice, there is no standard way to compute it. Right? Because cost is a very individual thing to a business, right? Depends on how you run your business, what class of business it is, whether you need space or not, what state you're in, what country you're in, what taxes you have to pay, what business laws you have to, right? There's so many things that would influence cost. It's just, there's no standard model for calculating it. You just have to look at all the things that you need to pay for and add them up. So that's not something you can just know off the bat. So whenever you need a cost function, I'm pretty much going to tell you. So it's always going to be a given function. I'm just going to tell you, here's the cost function. Another kind of function is the revenue function. mentioned above. Okay, so the revenue function, this is typically, you can calculate it, typically calculated by your revenue, R of X, is going to be the number of items sold, let's call that X, times the price per item. So if I sell 5 things for $2 each, my revenue is $10, essentially, right? So that's how it's going to be calculated. This, what you want to realize what it is, it's your earnings ignoring costs. So it's just the amount of money that you bring in. We don't care about how much it costs you to bring in that money, right? It's just the money that you bring in. This may also be given. Sometimes I'll give you the revenue function, but if I don't, this is how you calculate it. Find out how many things you sold for what price. The next important function is the profit function. Was mentioned earlier, but let's make sure that we know what this is. This is calculated by P of X is equal to R of X minus C of X. In other words, it's revenue minus cost. So here's your earnings after costs are accounted for. So you bring in a certain amount of money, but then you have to pay your laborers, you have to pay for materials, you have to pay for electricity. So that money that you bring in is going to dwindle. You don't get to keep all the money. You have costs that you have to pay out. So the profit is a measure of what you have left over after you've paid out all your costs, right? So you bring in a certain amount of money, you subtract all your costs from that money. What you have, the sum that you have left, is called profit. Okay, so that's how that is worked out. Another important function. There are 2 more. I think there are 2 more I want to do. Yeah. So there's a function called d of x. Sometimes it's actually called p, and this is called the demand function. So this guy, this gives the price at which consumers will purchase X items, right? So when the public demands, they want to get a certain product, we call that, like all the products that they want, the demand, right? And so the demand function actually measures the price at which people will demand things. So if the output of so if you plug in X equals 1 and your demand function outputs 10, what that tells you is if you price it at $1, people will end up buying 10 of these things overall. Well, the output would be the 1. We'll do more examples. I think I just said the wrong thing just now. But it measures the price, right? So you'd plug in the X would be 10 in what I just said, and the output would be 1. And that would tell you that, okay, if I charge $1, I can sell 10 reliably. So this is the price at which consumers are willing to consume. Now, there's another function that is kind of associated with this on the flip side. I'll call it here big S. And this is called the supply function. This gives the price at which suppliers are willing to produce X items. Okay, so that's the supply function. Now, those are all the functions that I want us to know. So there's cost, there's revenue, there's profit, there's demand, and there's supply. It's possible to construct a demand and supply function given some data, but a lot of times I'll also be given. So I could say something like, oh, the demand function is linear. And when I charge this price, I sell this much. When I charge that price, I sell that much. So basically, you just know I just gave you two coordinates on a straight line. You can find the equation of the straight line. That equation would be the demand function. So you can calculate it that way. So now, in economic theory, we have something called the law of supply and demand. You don't need to know it exactly. Essentially, this says d of x is always a decreasing function, while s of x is increasing. So if we were to plot these two functions side by side, and I were to plot the price on the horizontal, which is very typical, and I plot X number of items on the vertical, then if I'm looking at a demand function, the demand function is going to go down over time. While the supply function is going to go up over time. So it's also possible for me to give you two functions and I just say, hey, these two functions represent supply and demand, but I'm not going to tell you which is which. And you would need to figure out which is which. And the way you would figure out is figure out which one is increasing and which one is decreasing, right? So you can do that. And yeah, so now we usually don't think of these guys separately. Sure, the supplier and the seller will think of them separately, but we'll think of them separately, but we will often think of them together. Someone's coming in here. So normally we would draw on one axis both functions. Okay, so price and X number of items. And you would have a demand function. Come on, iPad. And you would also have a supply function. Get an iPad, they said. It'll be great, they said. Right? And so when you juxtapose them like that, you get a picture like this. Now, what is going on in this picture? You'll notice that they intersect at this point, but I want you to appreciate what goes on at each side of that. On the left, you'd realize that consumers are demanding this much. That's how much they want to buy at that price. But suppliers are only willing to produce this much. So people want more of the thing than is in the market. And this leads to something called scarcity. Right? Bad for consumers. People want to get stuff. They have the funds to get it, but they can't get it. You get scarcity. On the flip side, you would have your suppliers are willing to produce this much at a certain price, but the people demanding it would only demand this much at that price. So what ends up happening, you have more products in the market than people willing to buy those products. The products get stored on the shelves, no one buys them, and this leads to a surplus. This is bad for suppliers because you just spent a whole bunch of money hiring a whole bunch of people, paying a whole bunch of costs for stuff that no one's buying. Not great, right? Now, the fact that the supply and demand are increasing and decreasing respectively kind of makes sense in the sense that notice that there are more Toyota Camrys on the road than there are Lamborghinis. Why? Lamborghinis are more expensive. People have less resources. People buy less of them, right? The cheaper something is, the more people are willing to pay for it, the more people are willing to buy that thing. You'll have more of that thing being demanded in the market. Anyone wants a car, chances are the probability that they will get a Toyota or a Honda or something is a lot higher than the probability that they're going to get a Lamborghini or a Porsche or something else, right? Those are more rare. As the price goes up, people demand less and less. People buy less and less. So the demand function being decreasing makes sense. Supply function increasing also makes sense, right? Let's go back. I'm the guy making iPhones. Hey, Jhevon, I need you to make 10 iPhones next week for me. I'll pay you $5 each. Not really a good reason to get up in the morning, is it? Yeah, you know, I got this thing. I got to go, you know, the in-laws, you know, I got to go this, you know, do you say Thursday? Okay, Jhevon, I will pay you $1,000 per iPhone. Dude, I can make 10,000 of those things by next week, right? Now it's different. Once I can charge a higher price, I'm going to be willing to produce more because I can bring in more revenue. And so the supply function increasing with the price makes sense, right? However, you don't want to be on the left or on the right. What you want to be is right here, smack dab in the middle. This position here is called market equilibrium. The buyers match the sellers. The producers produce just enough and everything gets sold, everyone is happy. So it's good for the consumers, it's good for the suppliers. And so that is something that we are often interested in. We often seek market equilibrium and the price that achieves it, right? A lot of this market equilibrium has to do with the price. If the price is too low, you have scarcity because everyone's going to buy it. It's cheap. If the price is too high, you can have surplus. Not enough people are going to buy it. You want the price just right. And then you'll have the buyers matching the sellers. It's beautiful. Everything works in harmony. Everything is great. Yeah. So with the technical difficulties today, I don't think I'm going to get to any examples. But I will just leave the examples here and you guys can do it. In the meantime, I do have some more stuff to tell you. What else for my notes here? D of x and S of x are often given, but we can construct them. In class, I can give you directions on what type of function to build. In practice, D of x is done by market research. And S of x is calculated by supplier, how much money they want to make. Right. So that's what you need to know. Also, you should know, we can rewrite an old formula. Revenue can be thought of in a different way now. Revenue, R of x, can be thought of as x times D of x, right? So D of x does measure the price, right? So that is the price that I can reliably sell X items for. So if I tell you the demand function, or actually to build the demand function, and you need for some reason to find revenue, you would simply find that by multiplying the demand function by X, right? So that's, and this would be X equals number of items sold. So I'm describing all this because the problems in this section tend to be word problems. So you really need to understand the concepts behind everything. Because then when a certain thing is described in words, you want to know that you understand it. Sometimes D of X is actually called P. Time we have a couple minutes. All right. back to marginal functions. I think I just have one more thing to make. C prime of x is approximately equal to c of x plus 1 minus c of x, which shows c prime may approximate c of x plus 1 minus c of x. You may wonder why not just calculate c of x plus 1 minus c of x. Well, two reasons mainly. I did mention them earlier. C of x plus 1 may be very complicated. To figure out, not in this class, but in general. So just because you know how much it costs you to make a certain amount of things doesn't mean you'll know how much it's going to cost you to make slightly more. A lot of things can happen in the real world that will affect that. Two, c of x or c of x plus 1 cannot always be known. They may be in the future, etc. Right? I'm running a factory now. I want to open up a second factory. Can I really know for sure right off the bat all the costs that would be associated with that second factory? No, it depends on the location, the size, how many people I'm hiring, the local laws, what state I'm in, all that other stuff. So sometimes you want to talk about costs, and you might even have a kind of example to go by, but you can't know for sure. So that's why we need this. Now let's talk about examples. And at this point, I'll just paste them here. We're not going to do them. But I think you guys might know enough to actually try them on your own, and we'll pick up tomorrow with them. Let me find them. Okay, so I'm going to paste the examples here that I want you guys to try for next time. So there's one of them, example 1. Here's another one. There's example 2. We're only going to do 2 examples, but also I think after those examples, we'll have time to start the next topic. So what I will do is I will also paste here the handout for the next topic. So right after this topic, we're going to go into exponential growth and decay. You can read about that, and there are the examples. So if you have additional time, you can actually try to get through those as well. And we will do those next class. So we'll do these examples, move on to exponential growth and decay. Let's make these a little bit Okay, yeah. So these are the word problems. Try those. Okay. So I'll post these in the notes as usual. Take a screenshot now if you want. I'll leave it there for a few minutes. But that's all I have for you today. Try those questions, and we'll pick up with those tomorrow. Okay. All right, cool. Thanks for your time and attention. Enjoy the rest of your day. I will see you guys in the next one.